Hi everyone. This is a short video regarding binomial expansion. So I'll start with the Pascal's triangle. In the Pascal's triangle, the way that we construct the Pascal triangle is very easy and interesting. What you do is you write the sum of each two numbers in the middle of that in each layer. So layer 2 has 1, 2, 1, and layer 3 will have 1, 3, 3, 1. Layer 4 will have 1, 4, 6, 4 and 1, and finally I have just written up to the fifth layer, and you can see how it is constructed. Now what does this bring? You might have expanded a plus b whole square, and we all are quite familiar with this formula, a square plus 2ab plus b square. These numbers, these coefficients of these terms are where Pascal's triangle comes very handy. Look at the coefficients: 1, 2, 1, 1, 2, and 1, right? So from Pascal's triangle, we are obtaining the coefficients. As for the binomial expansion is concerned, this is a general way of writing binomial expansion. I'll explain in detail. But before that, I want also to discuss about factorial. What is a factorial? Factorial is simply, if it's 5 factorial, it means the product of all the numbers below 5, including 5 up till 1. And so what we do is, if it is 5 factorial, 5 times 4 times 3 times 2 times 1. And if it is n factorial, just keep on reducing this n by more and more number each time, n minus 1, n minus 2, until it reaches 1 here. We will also have some questions related to division or multiplication of factorials, especially for division of factorials. The ideal situation is, if you have a question like that, you would want to break down the bigger number factorial. Like 7 factorial can be broken down to 7 times 6 times. All of that 5 times 4 times 3 times 2 times 1, I'm not writing that. And instead, I'm just writing it as 5 factorial. And why did I do that? So that 5 factorial, the lower number of the factorials in the question can easily be cut out, and there we are. You would want to break down the bigger factorial number up till this small number and do the cancellation. Then the application of factorial comes into this combinations. This is under the heading of counting principles. It is written in both ways, NR or NCR. It's in the N combination R, and it's defined as N factorial over R factorial times N minus R factorial. For example, 5 combination 3 is 5 factorial over 3 factorial times the difference of the two. And this can be again simplified as 5 times 4 times 3 factorial, so that you can cancel out the 3, and 5 4 is 20 divided by 10. Just this much for factorials and combinations. And we can show this Pascal's triangle as this: n0, n1, and n2. Basically, n is 2 here, second layer, so it's 2, 0, 2, 2, 2, 1, and 2, 2. Similarly, for third layer, you would write 3, 0, and that will give us 1. In fact, any number with the n with a 0 combination, it's 1. Then it's 3, 1, which is 3 itself. So n1 is n. And similarly, last one is 3, 3. And that's also a result that n combination n is 1. So we have these results. I'm going to jump to our next part, that is expanding in descending powers of x. Descending means starting from the highest to lowest. Descent, like descendants of God, they came from above to earth. So descending powers of x means the highest power of x first. So as I mentioned earlier, using the Pascal's triangle, if I am expanding it, this binomial means having two terms. It's a polynomial with two terms in it, and we are expanding it up to the power 4. So I constructed the layer 4, and look at the coefficients: 1, 4, 6, 4, 1. I got these coefficients from the fourth layer of the Pascal's triangle. And then I'll start with x, which is my first term, and I'll start with the highest power involved. So x to the power 4, x to the power 3, x to the power 2, x to the power 1, and just to show you for understanding, x to the power 0. And for the second term, the same procedure continues in the opposite direction. So you start from 2 power 0 and go on increasing. 2 power 0, 2 power 1, 2 power 2, 2 power 3, and finally 2 power 4. And then which you always can simplify as x power 4 plus 8x cubed plus 24x squared plus 32x plus 16. So that would be termed as the expansion of x plus 2 whole power 4. And this is written in descending powers of x from the highest to the lowest. Sometimes the examiner may ask you, write the sum of the first three terms, or just the first three terms in the expansion of x plus 2 whole power 4 in the descending powers of x. So that is something to be considered. Slight level of difficulty is raised if we have numbers other than simple x, like there are multiples of x, or you can have fractional terms as well. But the procedure continues the same. You still use the Pascal's triangle for making the coefficients, and then first term with descending powers, and the second term with ascending powers from maximum to minimum and minimum to maximum. Important to note in this question is, in this example is, that if it's a negative in between, you will start with the positive term, the first term, and then you have to get alternate signs. So positive, negative, positive, negative. You must remember alternate signs for a minus b whole power n. For positive, it's no issues. We are not considering the signs here. Going further, expanding in ascending powers of x. The trick is very simple. If you want to keep track of ascending powers, like ascend means going up. So you would want to make x as your second term. Instead of a, b, or x, y, if you learn that this is the first term and this is the second term, it's much more convenient to communicate. We have 2 as our first term. We take the coefficients from the Pascal's triangle, 1, 3, 3, and 1. We go for 2, starting from the highest power and downwards. So 2 power 3, 2 power 2, 2 power 1, and 0. Similarly, x to the power 0, 1, 2, and 3, which simplifies to 8 plus 12x plus 6x squared plus x cubed. So this is the expansion expressed in the ascending powers of x. It's not very difficult and it's not very different also. You can do the regular x plus 2 expansion, right? Starting with x cubed, but then you would reverse the order of all these terms. And that also serves a purpose. Okay, our next bit for the binomial expansion is its application, and we can use it to evaluate certain powers of some numbers. For example, I've used the example of 2.2 to the power 3. And we might probably have to show working for that. Nevertheless, we have x plus 2 whole cubed using the Pascal's triangle. The coefficients are 1, 3, 3, 1. X to the power 3, x to the power 2, x the first term that is. So are 1 and 0. And similarly for 2, it's 2 power 0, 2 power 1, 2 power 2, and 2 power 3, which is simplified to this. So this is a simple question of giving the binomial expansion. But if we have to use this, hence is an important command term. When the examiner says hence, it means you have to use the previous result. If you are going to find the value of 2.2 whole cubed, and you have to use your previous result, what does it mean? Can I break 2.2 as 0.2 plus 2? And looking at the question above, I know my x is 0.2. I've already expanded, and so I just need to plug in x equals to 0.2 in all these places where x is occurring, and that should give me the answer. Going up to binomial theorem in the next video.